my screen as well, and a little bit followed along with what I'm talking about here. This is extremely important. Okay, actually most of today is extremely important. And I am recording this as always, so you can go back and refer to it later. I added a course announcement this morning because we just got directions on how we're going to do our EPA testing. It is very important you guys read my announcements because a lot of the questions I'm getting in email, a lot of the questions I'm getting in messaging on Canvas, I've addressed in my course announcements. So sort of obvious people aren't seeing them or aren't looking at them. Please read my announcements. Okay, EPA testing, okay, is going to happen the week after Memorial Day. That's the week of the 26th, 27th, 28th, and 29th. Okay, we are going to be covering EPA starting next week. I think we go into it on Tuesday. So we start with core, then we do type 1, type 2, and type 3, and I break it apart over 4 days. Now, when we're in a classroom environment, okay, we do it the exact same way. There's no change here on how I do this. The only thing that's a change is I cannot look at you, okay, and I cannot tell if I'm losing you someplace in the EPA conversation. Okay, EPA is relatively boring, has a lot of information in a very short time. It is a very high-stakes test, and I don't like high-stakes testing, okay? But I have to tell you, folks, this is an extremely important exam. You have to pass it once in your career. You never have to deal with it again, but I need you to pass it, and I need you to pass all 4 parts of it. Okay, the EPA exam is 100 questions long. It has 25 questions on type 1. 25 questions on type 2, 25 questions on type 3, and we'll go into what all of those are, and then 25 questions on core. You have to pass core and whatever type in order to get the certification for that type. If you pass all 4 sections, and I think the passing is a 70 on it, but if you pass all 4 sections, you get a EPA universal certification. In other words, you are not restricted on any type of refrigerant or refrigeration system that you can legally service according to the federal government. Now, this is not a state license. Okay, this is the federal government saying, we have trained you and you have passed an exam on the safe and proper handling of refrigerants. The exam has been modified in recent years to handle the new refrigerants and new refrigerant guidelines. I urge anybody who's using Quizlet.com and a lot of these online study sites, and I'm fine with using them. I've never said don't use them, with the exception of this exam. The information on those sites don't anymore match this exam. Okay, the exam has changed. I know some of you do work with flashcards. I know some of you create your own flashcards. I urge you to share them as you're creating them. If you want me to check them before you start studying from them, just send me the link. Again, I have no problem with you folks doing that. But the one thing I want to caution you on is don't use the study material that's currently out there on the internet. The exam changed last year. Okay, and it's still too new. People haven't put the correct information out there yet. At the top of your course, in course announcements, okay, I have put in the course overview module. And again, if you're using the app, you got to go find this, okay? I have put the EPA student manual. Okay, it's called EPA Manual, download and study. I've also put a copy of the online testing guidelines that we are going to have to test by. Okay, those 2 things are out there. I need you to, A, read the online testing guidelines and realize that's why we're handling it the way we're going to be handling it. Okay, we're under some pretty tight guidelines on this one. Okay, the EPA manual, start looking at. Okay, this EPA manual was written by the company that actually wrote the exam. Okay, and there's very little in that manual that is not on the exam. Now, if I said, okay, I'm trying to figure out how to explain this properly. The manual has the facts, okay, has what you're supposed to do, has different types of refrigerants. Some of the exam questions, and this is going to be very important to understand, some of the exam questions are situational. In other words, you're going to have to take one or two facts, put them together to come up with the answer. Okay? This is a closed book exam. There is no time limit. You will be allowed to have a scratched piece of paper, and you'll be allowed to have the temperature pressure chart and a calculator. Okay? Again, we're going to have to give this exam. You're going to have a one-on-one exam testing session with an instructor, with an HVAC instructor. That will be scheduled. I go over this all in my announcements. It might not be me giving you the exam, okay? Because, again, it's a one-on-one, and I have to get about 80 people through these tests. Doesn't matter who the proctor is. It's going to be the same thing. You're going to sit there with your iPad. The proctor's going to ask you, because we have to record these sessions, the proctor's going to ask you to look at the camera and hold up some sort of picture ID to prove that it's you, in case somebody looks at the recording. We're going to start your testing session for you. We're actually going to give you a link, and you have to leave the video camera on, even though we know it's going to be staring at the ceiling, but that's what it is. And you're going to have to leave the sound on, so we make sure you're not asking people in the background questions. This is something you can't phone home on. When you schedule the session with the instructor, okay, that's with the proctor, make sure you schedule for a time of the day that you actually will have some peace and quiet. You're not going to be allowed to have a lot of noise around you. You're not going to be allowed to have people running in and out of the space. So just please, I know some of you have kids. I know this is going to be a problem, but please take that into account when you're setting up times with the proctor, who's, again, you're not going to get contacted today or early next week. It will be sometime late next week, okay? Any questions?
Chris.
Yes.
This is Barry.
Yeah.
Can I say something?
Sure.
Okay. For everybody that's going to take this EPA test, this is no joke. You have to study. This is going to be the hardest test in your whole career. I don't want to scare you, but at the same time, be scared. You have to study. You're not going to be able to take your way out of this thing. Okay?
Okay, somebody is unmuted. Do you have a question for us? Or?
Yes. Is this test basically on refrigeration?
It's the refrigeration laws, how to handle the different types of refrigerants, and the test, again, has been rewritten last year. Actually, 2018 it was rewritten, but it started coming out last year, and it includes propane-based refrigerants, which we haven't talked about yet. We're going to talk about next week. But, yes, it is all about the refrigeration cycle and refrigerants. So everything we've been doing up until this point has an impact on the test. Does that answer your question?
Yes.
Okay, any other questions?
What happens if you don't pass it the first time? Can you retake it again?
Absolutely. What happens is, for example, let's just say out of the 4 parts, you pass core and type 2. Okay, you will be allowed to retake it with the original proctor. Okay, that's the key. You'll have to make an appointment with the original proctor. You'll be allowed to retake it, and you only have to take the parts you didn't pass. Okay, Does that help?
Yes, it does. It's good to know that you don't have to retake the entire test, just the parts that you didn't pass.
Yeah. Now here, again, the key is you'll have to make an appointment with the original proctor. And the other key is that you don't want to go through that if you can avoid it. We've had a pretty good pass rate as long as students put their mind to it and study. Okay, 90% of our students do get universal on the first try. Okay, so it's just a matter of taking the time. That's why I'm giving you this manual early. Okay, the earlier you start looking at this, the better off you are. You will also see that over the next couple days after this weekend, the workload on other assignments is going to come down. Okay, I really want you guys to concentrate on the EPA. Anyone else?
Is it all mashed together, or is it separated into sections?
Separated out. You'll do the 1 through 25 is labeled core, 26 through 50 is labeled type 1, and so on and so forth. Type core is general safety. Type 1 is small appliances like window air conditioners, water coolers, and stuff like that. Type 2 is your split systems, your rooftops. And type 3 is low pressure. We haven't talked about that yet. Low pressure. But it's really neat to get the universal on the first try. That's a good goal. Okay, any other questions on the EPA?
When should we start studying?
I would recommend as soon as possible. The first thing I do, if I were studying for this exam, okay, and a matter of fact, since I did study for this exam years ago, what I would do is I would take the manual, okay, that I have out there. It's again in the course overview. You'll find it where my screen is right now. I would take the manual, and I would not mark it up on the first read through. I'd read through type core, then I'd read through type 1, I'd read through type 2, and I'd read through type 3. I'd have a scratch piece of paper next to me, and anything that you don't understand, toss onto the scratch piece of paper. Then I would go back through it, okay, and I would do a second read through, possibly with a little bit of highlighting, possibly, I mean, you guys have been in school long enough, even through high school and stuff, you guys know how to highlight and to find the core concepts, okay? Then I would also, once we start our lessons, which will be Tuesday of next week, I believe, okay, you'll also have the PowerPoints. I'll make sure you have the full PowerPoint set. You'll want to study those as well. Between the manual and the full PowerPoint set, you will have the information, every bit of information you need to pass that test. But asking questions as I go through it is going to be critical. As Barry did talk about, okay, this is a critical exam. This is a tough exam. Okay, it was written by the EPA to U.S. Navy specifications. They used the same exam in the Navy, okay? They didn't make it less difficult for us, okay? They tried, but it wasn't changed, okay? It's a single exam that's used across all government agencies and all technicians going into the trade. Just be aware of that, okay? Unlike prior versions of this exam, dates don't matter as much. And Barry, that's probably a difference from when you and I took it. There isn't as many dates on it, okay? And that's the biggest difference. It more has to do with operation and what you're doing with the refrigerants. So there's some pretty big differences on the exam from prior versions, which is why I'm saying do not study based on Quizlet.com and those for this exam. It's too new. They haven't gotten the right answers out there yet. Okay, and I encourage study groups. I 100% encourage study groups.
Hey, can I say something akin to that?
Yeah.
So I sent a message to everybody in this course, and I have heard from 2 people that are interested in the study group.
Cool.
Pardon me?
I said cool.
Yeah, so 2 is great. I talked to one of them, and it looks like 6:30 p.m. is going to work. If there's only 2 people, I want to stick to one time so we are all on the same page. If more people are interested, I sent you a message on Canvas. Please respond. Please tell me what you want to get out of the study group.
Guys, that's a very good offer. Okay, study groups are awesome if you have time to do it. I know some of you may not have time, but again, this is a very high-stakes exam. I don't like this type of testing. Okay, I sort of despise high-stakes exams, as you can probably guess from the way I grade things and stuff like that, but I just this one I have no choice on. So, okay, I do need to move on with today's material. If you have questions, please go ahead and you can email me questions. Guys, try to keep it to email. Text is difficult for me because I can't include a lot of additional information if I need to link things in from my laptop to text messages. It's a problem. So, okay, I need to talk about evaporators today. We can't avoid this conversation. I'm already a day behind on it, and I can't go into next week's conversations without having done this evaporator session. So we're going to talk about evaporators. Okay, there's 2 primary types of evaporators. Okay, we have natural draft and we have forced draft. Okay, 2 primary types of evaporators in air conditioning, natural draft and forced draft. Quite frankly, the primary one you're going to see in air conditioning is our forced draft, but we also have to know what natural draft is. A natural draft evaporator depends on gravity for air circulation. Gravity circulation occurs because cold air is denser than warm air, and cold air will sink, warm air will rise. Okay, so we can create circulation around an evaporator coil mounted on the ceiling. Okay, so we have an insulated ceiling up here. We have our tubes of our evaporator coil. We have a drain pan for the condensate drains, and we have the cold air falls, the hot air rises, cools, and falls off. Where would you think you would see this type of system?
In larger commercial buildings?
In a freezer?
Both are very valid answers. Okay, in a freezer you might see it. Okay, in a large, like if it's an entire cold warehouse type freezer, okay, you would probably see it there. Where would you see it again in air conditioning? What type of business would I see this in?
Grocery stores. A butcher shop.
Yeah, all of those are valid. It's going to be in a business where we have to maintain a cold environment, and we're really not all that worried about appearance. Now, grocery stores have now gone to rooftop units. You don't see this that often anymore. What about if I had a air-conditioned storage warehouse or something like that? Okay, it might be in there. This is older style air conditioning, okay? It's very inefficient, it's very messy, okay? And it just doesn't make a lot of sense anymore, okay? There's too much new equipment out there that replaces this. So just be aware, this isn't a popular way of air conditioning anymore, but again, some commercial buildings still have it. In freezer, frozen food warehouses, frozen food, you're likely to see systems like this. But in air conditioning, it's not very popular. Okay, forced draft evaporators have basically replaced the natural draft evaporators, okay? That's what we have. It's an evaporator that's equipped with a fan. The fan blows air over the evaporator coil, okay, and it does heat exchange with the coils, with the refrigerant in the coils. The coils are usually enclosed in a metal housing. Okay, this is just a window unit. Okay, we basically pull air in, we blow it across a coil, and then the refrigerated air comes out. Okay, so this is what we're basically doing. Okay, forced draft evaporators is what you're probably most often going to see. The major types of air-cooled evaporators are fin and tube, plate, or microchannel. The most widely used one, the one you're going to see most often currently, is the fin and tube evaporator. Okay, all it is metal fins of different styles connected to evaporator tubing. Now, you're also going to see occasionally the plate style, the plates, okay, which is sort of this picture. Not very often, okay? This, if you see it, just realize it's just another type of evaporator. This doesn't have as much airflow capable, and if one of these gets clogged up, it gets pretty bad. Some of the common combinations of material used on evaporator: copper tubing with aluminum fins. This right now is by far the most often used. We rarely see copper tubing with copper fins. Why don't I see that anymore?
More expensive?
It's more expensive, yeah. Aluminum is much cheaper. Aluminum also has a better heat exchange capability. So the copper tubing with aluminum fins. Steel tubing with aluminum fins. Okay, you only see this really with ammonia systems. R717 or 717 is ammonia.
Is that because of how corrosive the ammonia is?
Yeah, ammonia eats away copper. It's a bad thing. Okay, so I can't use it with copper. Okay. Fin spacing varies. Okay, for natural draft evaporators, the fins are spaced between 1/2 inch and 1.5 inch apart. Now, when we start blowing air through it with forced air evaporators, the spacing changes. Okay, it gets smaller to 1/16 to 1/4 inch for forced draft evaporators. The spacing of the fins impacts, okay, the amount of surface area exposed to the air that is being cooled. Manufacturers can adjust the cooling ability of an evaporator by changing the spacing and the number of fins. Okay, so the greater the surface area in an evaporator, that's not the greatest the holes for air to flow through. That's the greater the surface area, the more cooling capacity I'm going to have. Okay, that's why forced air evaporators, okay, the fin spacing is much smaller than natural draft, and that's why there's an efficiency difference. Okay, the smaller the fin spacing, the larger the surface area. The more fins I can fit in there, the higher the cooling capability. Fin spacing is also adjusted to compensate for the depth of the coil. Okay, again, the deeper the coil, in other words, how wide the coil goes, the greater the fin spacing. I want to make sure that all the air blowing through the evaporator has a chance to sit on the fins, has a chance to come in contact with the fins. Evaporators that have a 6 to 8 inch depth, that's a pretty narrow evaporator, usually have about 1 inch spacing. Those to 18 to 20 inch depths go up to the 1.5 inch spacing. Again, that now, is that going to be natural draft or forced draft right there?
Forced draft.
Look at the fin spacing.
Natural draft.
Yeah, that's going to be, those two last ones are natural draft. Fins are too wide for forced draft. Fin spacing of 1 inch or less. We're starting to get into natural draft or forced draft. Fin spacing of 1 inch or less decreases air turbulence. The tubing is normally 5/8 inches OD. Okay, that's very important. You need to remember that. 5/8 inches OD is the normal tubing size. That's outside diameter. 3/4 inches OD is used on large evaporators. Okay, and it's usually used on the tubing size of 3/4 inch OD is usually used on the manifolds if you have multi-pass evaporators. Okay? And again, this is just an example of an evaporator, 2 different evaporator coils. The fin spacing. Which one do you think has a better heat transfer rate? There's 2 evaporators on this picture.
The one at the bottom?
Anyone else?
The one up top because it has more fins.
Yeah, as long as the same amount of air is blowing through it, the one on the top is going to have greater heat transfer because of the number of fins and the air being forced through it. The one on the bottom, though, is going to allow more air through. Okay? Now, what we don't see is the rest of the picture of this evaporator. Okay, I don't know what's going on over to the left or the right side of this. I see the full evaporator at the top. Depending on the size of this bottom one, it could be the same, but it's much larger because of the fin spacing. Questions on that? It's all about surface area. Now, there's 2 different types of operating designs. Direct expansion. The refrigerant is in the evaporator and directly cools the air. The evaporator coil is full of refrigerant and air is flowing across the coil. When you look at manuals, okay, you're going to see the letters DX. Sorry about my mouse scribble here, but it is what it is. DX is direct expansion. Guys, I'm going to mute people here, sorry. DX is direct expansion. Means the refrigerant is in the evaporator coil. The air is blowing across the coil. That's where my heat exchange takes place. Indirect expansion. Refrigerant cools a secondary medium such as water or glycol. That cooled water or glycol flows through the coil that cools the space. Let me say that again. In indirect expansion, the refrigerant cools a secondary media such as water or glycol. The secondary medium, which is the water or glycol, flows through the coil in the airstream that cools the space. Big difference between the 2. Okay, the bottom one is sometimes known as a chiller system or water-cooled system. Basically, we have a chiller barrel someplace in a mechanical room someplace. Okay, that chiller barrel cools the water, and then we pump water around the building, and we have air handlers that are taking off that water feed. Okay, primarily the top one, residential, light commercial rooftop units. Bottom one, heavy industrial areas, office buildings, anything that has a chiller with cooling towers on the outside. Okay, big difference between the 2. Does anybody have a question here? Okay, And again, indirect expansion, chiller barrel down in the bottom, chilled water evaporator, compressors cooling that chiller barrel, I circulate water. My water temperature is in the 40s normally. I don't normally circulate water in the 30 degrees point. It's normally in the 40 degree point, someplace. Two types of direct expansion coils exist, the dry type and the flooded type. The dry type uses 25% less refrigerant than the flooded, has more vapor in the evaporator, has less chance of flood back to the compressor. The dry type has a disadvantage. It's slower to do what we call a pull down with heavy loads. The pull down is that initial startup where the evaporator gets cold, okay, in order to start cooling the air. So when I first start my system up, the evaporator isn't cold. Okay? Systems run with higher head pressures. Okay, head pressure, high side pressure. Again, realize when we talk about head pressure, we're talking about any pressure between the outlet of the compressor, that's the discharge line, and the metering device. High side pressures are head pressures. There's two purposes of evaporators, cooling and dehumidification. The cooling changes the sensible heat content in the air. This I can actually measure. By now this should be pretty clear because we've talked about this a lot. Sensible heat, heat I can measure. Dehumidification changes the latent heat and the moisture in the air. Okay, this process is described in the psychrometric chart. We want to keep indoor humidity under 50%. Specifically for my York group, why do I keep indoor humidity under 50%? Come on, guys.
With mold.
Mold. The reason I said specifically for my York group, you guys have, for the most part, had design. Okay, and I know it. Okay, so again, indoor humidity under 50%. At 50%, I start growing mold. Okay, evaporator design is going to be done by mechanical engineers. You're going to have a catalog to choose evaporator and condenser combinations. Okay, it's based on cooling requirements and size. And again, for those of you who have had design, you've already done this once. For those of you who are going to have design as your next course, you will be doing this. Okay, so we have a catalog. We choose the evaporator and condenser combination based on cooling requirements and size. There are two factors that need to be looked at for evaporator design. We have pressure drop and we have evaporator capacity. Can someone define pressure drop for me? What causes pressure drop? Wrong answers are okay.
What atmosphere conditions?
Let's look at within some device. Okay, so if I have a long set of tubes, what causes pressure drop?
The longer the tube or the shorter the tube?
Longer the tube. Do bends cause pressure drop?
Yes.
Yes.
Yeah. So any restriction to refrigerant flow or water flow causes a pressure drop. Okay? Pressure drop. Did I talk about it a little bit when I talked about TXVs yesterday? Okay, pressure drop. If the evaporator is too long, and if I go over 2.5 psi pressure drop, okay, I have to have a third port on a TXV, which has that balancing port. Okay? So pressure drop makes a big difference in evaporator design and selecting the correct evaporator for the system. Evaporator capacity. Why do I care about evaporator capacity with compared to my condenser? Why does it matter? Anybody? Why does it matter?
I guess it's the size to determine how much heat it can take.
So you can keep up with loads, I guess?
Yeah, all of that. But we also have to be very careful because my outside unit, which is the condenser, the size of the compressor, the size of the condenser coil, has to match the amount of heat that can be absorbed by the evaporator. Has to match. Okay, very specifically match. That's model numbers, okay, size, and airflow. We have to match the indoor and the outside unit. That is going to be one of the biggest issues that you guys see in terms of when somebody replaces half a system and then you have to go back and service it. May never work right because the two never matched. Causes of pressure drop, I've already said it. Long evaporators. Not the actual size, but the length of the run. Okay, I can use a distributor in the evaporator, and I can use multiple evaporator circuits to lower that pressure drop. Tubing too small. Okay, if the evaporator was built with tubing that was too small for the application, someone selected the wrong evaporator. Okay, it can cause large pressure drops. So again, when we're talking about a split system, we're talking about that coil that sits on top of the furnace. We have a liquid line, we have a gas line. We bring in return air. We have a blower someplace in here. We blow the air up through to the supply ductwork. Supply ductwork supplies the house. Return ductwork pulls return air back in from the house and recirculates it through. All the air blows across this evaporator coil. Who knows what the temperature difference between the return and the supply air should be? It's already been in your reading someplace. The temperature difference between the return and supply air. Anybody know what it is? Rule of thumb.
15 degrees, 10 to 15.
20.
About 15 to 20. Now, when can I see it under 15? Yeah, on a very humid day, it can drop a little bit lower, but we want between 15 and 20, and that's going to vary depending on equipment size. Okay, 15 is perfect. 20 is very good too, but I also have to make sure that I'm not oversizing my systems either. Okay, because if the system's oversized, it's not going to dehumidify properly. Okay, indoor humidity takes a large percentage of my cooling load. Poor evaporator design has what we call a low gas velocity. Okay, there's poor oil return. Okay, there's no scrubbing effect. In other words, if there's not enough air movement at a fast enough rate, if the refrigerant isn't moving through the coils fast enough, debris is going to build up in the evaporator tubes. Okay, it's called an oil-clogged evaporator. The oil sits in the evaporator and it never returns to the compressor. Okay, if there's not enough speed, not enough velocity on that refrigerant going through the system. Things that affect evaporator capacity, we've already talked about them. Surface area, temperature difference, refrigerant velocity, conductibility of the metal, that's how fast heat moves through the metal thickness, and the air volume. How many CFM of air do I have to have per ton of air conditioning? Again, some of you should know this. How many CFM of air per ton of air conditioning?
Like 450?
400. Very close. 400 CFM. And that's an F there. Sorry about, again, my mouse scratch. Okay. 400 CFM per ton of air conditioning. How many BTUs per hour is a ton?
12,000.
12,000. Okay. Microchannel evaporators, just like microchannel condensers exist. Inlet and outlet into a manifold. Every one of these rows coming down is a microchannel. Very small channel for refrigerant to flow. Extremely efficient evaporators. Too bad if it gets a hole in it, you can't fix these. You have to replace the entire evaporator. Okay. Microchannels, they're more compact and efficient than the fin and tube evaporators. They have a fluid passage that's less than 1 millimeter in diameter. They're surrounded by tightly packed fins that have very great surface area for heat transfer. Unbelievably efficient pieces of equipment. The biggest problem is they're extremely expensive. Most of them are made of stainless steel or aluminum. Aluminum is very frequent. You cannot braze these. Once they leak, you can't do anything with it except toss it in the recycling bin and start over again. Okay? These evaporators are made of what we call extruded aluminum to create small passages through a flat tube. Refrigerant flows through the header into the small holes. By using flat tubes, the microchannel evaporator has more tube surface area. Contact is fins, which increases conduction. Again, very, very efficient evaporators. Okay, microchannel evaporators are 30% more efficient than the traditional fin and tube evaporators. Their size can be smaller and have the same cooling capacity as a large unit. Okay, again, just a cutaway of the microchannels. Now, again, the problem is these are aluminum. Okay, for the most part, you can't braze aluminum. Okay, you're going to talk much more about that when you do your piping, but you cannot braze aluminum. And the paste they sell in Home Cheapo doesn't work too well. Okay, superheat. It's part of our evaporator. Okay, think about the refrigeration cycle when we talk about evaporators. We come in as a low-pressure liquid with flash gas. We start absorbing heat, which boils off the refrigerant. Once the refrigerant is all boiled off, the remainder of the path back to the compressor, we are gaining sensible heat. That sensible heat gain is superheat. It's the difference between the boiling point of the refrigerant and the suction line temperature. I went over this on the chart we looked at yesterday. Superheat is used to check if the evaporator has a proper level of refrigerant. Superheat is gained in the evaporator. Refrigerant picks up additional sensible heat after that change of state takes place. Change of state, liquid to a gas. But then we start absorbing sensible heat because the gas is still colder than the surrounding space. Okay, so we have a basic refrigerant design here, okay? We come in 40 degrees all the way through our change of state. Okay? After we do our change of state, we start at this point increasing sensible heat. Okay, so 40 degrees is my change of state. I'm at 50, 55. Okay, my gauge always tells me the temperature of my change of state. So I've taken a thermometer, and I've taken a suction line reading, and I've taken my gauge reading, I've converted it to temperature, subtract the two numbers, I now have my superheat. Okay, there's two types of superheat. Okay, I have system superheat, and I have evaporator superheat. System superheat is I'm taking my temperature at my suction line where it goes back to the compressor. That's system superheat. So if I'm standing outside at the outdoor unit and I'm taking my temperatures and pressures in the same place, that's system superheat. Okay? Evaporators. What?
I'm sorry, Chris. What's the equation for getting the superheat?
Okay. Low side pressure. And unfortunately, I can't. So you take your low side pressure, convert it to a temperature.
Yep.
Then subtract that from the suction line temperature.
So it would be 13.
No.
No, it would be
15.
15.
Okay. For system superheat.
Okay.
For evaporator superheat, you take your temperature at the outlet of the evaporator.
So it would be 10.
Would be 10. Okay, two different superheats. Which is more important to me as a technician? Which do I really care about the most?
The system superheat?
Yeah, I care about most the system superheat. I don't know anybody who's going to go take apart an evaporator or crawl into an attic to take an evaporator line set temperature unless there's a problem. Okay, I care about that system superheat because it lets me know if I'm getting refrigerant back to that liquid refrigerant back to that compressor. Okay, but be aware there are two superheat numbers that you will see referenced. System superheat, you're taking the superheat at the same point as the refrigerant goes back to the compressor that you're taking your pressure, that your outside unit. Evaporator superheat, you're taking your temperature at the outlet of the evaporator coil. Two big differences. But I care about system superheat. Normal superheat, 8 to 12 degrees. I gave you this number yesterday when we were talking. Anybody on your simulators yet get anything different than 10?
Yeah, I'm having trouble with the simulators.
If I get through this early enough, I'll go into the simulator real quick, okay? But there's about 3 or 4 videos out there on how to get into them. But I will go ahead and I will go into it briefly here when I'm done with this. Okay, 10 degrees is the superheat that your simulator system has when it's running properly. You haven't seen that yet, you just might want to make a note of that. Okay, depending on the application, this can be lower or higher. Okay, but 8 to 12 degrees is the average, 10 degrees is perfect. If the superheat is high, I have what we call a starved coil. I don't have enough refrigerant in the system. If the superheat is high, I have a starved coil. I have a low level of refrigerant. If the superheat is low, I have a flooded coil. Okay, too much refrigerant. Now, when I put notes in capital letters, there's a reason for it. Do not adjust refrigerant with just the superheat unless you're sure you know how that system is working.
Is that 8 to 12 standard for, like, is that accounting for the different types of refrigerant, like the two main types?
Oh, yeah. It's not going to change based on your type of refrigerant until you go to a low-pressure system, one that runs under atmospheric pressure. But for 90% of the systems you're working on, that 8 to 12 is standard.
All right.
Now, again, there are exceptions, okay? So just be aware if you see a 5, it may not be wrong. Okay, don't adjust refrigerant unless you know how the system should work. Why am I saying that? What else controls refrigerant in a coil?
The airflow. Coil.
What was that?
The airflow across the coil.
The compressor.
Airflow is right. Let's skip the compressor.
TXV.
Thank you. TXV. Okay. You might not have a bad refrigerant flow. You might have a problem with the TXV. Okay. So don't adjust refrigerant unless you know how the system works. Here's why. Okay. Does refrigerant ever get used up?
No.
No.
So if you have a perfectly running system and it was installed perfectly running and you know there's no leaks, is it likely it's going to be a refrigerant charge problem?
No.
No. Okay, very important. Too many techs don't understand that. Okay, complete vaporization of the refrigerant should occur around the last bend of the evaporator. Any additional heat absorbed is superheat. The TXV as a metering device, which we talked about yesterday, is designed to maintain proper superheat. To measure superheat, take the temperature of the suction line with a thermometer. Okay, if we're looking for evaporator superheat, you do it within 6 inches of the evaporator. You take the suction pressure and you convert it to the temperature, which is the temperature of saturation. That's your boiling point, basically. That's the temperature of the change of state. Subtract that saturation temperature from the suction line temperature. So for an R22 system, if my suction pressure is 68.5, that's 40 degrees. Suction line temperature is 50. 50 minus 40 is a superheat of 10 degrees. Anybody have a question on this example? Okay, now there's a rule of thumb. If your condenser is over 8 feet away, you add 2 psi to your suction line, to your pressure, okay? So if you're very far away, it tells you to add 2 psi. Now, for those of you who have temperature pressure charts close by, does 2 psi do anything to your refrigerant readings, to your conversions?
No, not really.
Not really. Just do me a favor, as you go into your EPA exams, could you guys remember this? If the thing is over 8 feet away, add 2 psi. Okay? 2 psi is, when you get into the field, 2 psi doesn't mean squat. But when you're taking an exam that might have that question on it, it means 5 points. Okay? Domestic and commercial units. This is also applicable to refrigeration. Same rules apply. 8 to 12 degrees superheat is a rule of thumb. Whatever must be done to superheat, the opposite is done to the refrigeration, and I'll explain this. If you have a superheat of 20 degrees, the superheat must be lowered. So you have to increase the refrigerant charge or the flow of refrigerant. Again, if you have to lower your superheat, you have to increase refrigerant flow. If you have a superheat of 2 degrees, the superheat must be raised, so the refrigerant charge or flow must be decreased. Does anybody have a question on this? This is important. This is what you're going to be dealing with, troubleshooting. Again, if you have to lower the superheat, we have to increase the refrigerant in the evaporator. If we have to raise the superheat, we have to decrease the refrigerant in the evaporator. It's exactly opposite. Sounds like an awful good question of the day for sometime next week. Anytime you make a superheat adjustment, you have to wait 10 to 15 minutes prior to making the next adjustment. We need the system to do what we call stabilize. You can't just make adjustment after adjustment after adjustment. It takes time for the system to stabilize. With a fixed orifice metering device or a cap tube, there's nothing you can adjust. Adding refrigerant charge lowers superheat. Removing refrigerant raises superheat. Just make sure all your coils are clean before you do this. Adding charge lowers superheat. Removing charge raises superheat. Guys, if you're ever on a system and you come to a situation with a cap tube or a fixed orifice system that you have to remove the charge, before you do anything with refrigerant, go find the problem. There's another problem out there someplace. Probably a block coil. Why do I say that? Why do I caution on removing charge on a system?
Opening up the system.
What was that? What was that? I didn't quite hear.
Getting moisture into the line.
Yeah, you opening up the system.
Yeah, I'm opening up the system, but there's something else. Does refrigerant, just like we know refrigerant doesn't go away on its own, does refrigerant locked in a tight corner in the dark someplace make a little bit more refrigerants?
Sure.
Not really, right? There's nothing there that's going to multiply refrigerants in a system. Okay, so if you end up with a system that's suddenly overcharged, is it likely that I have too much refrigerant, or is it more likely that there's another problem someplace?
Another problem.
Yeah, you see where I'm going with this? Refrigerant doesn't multiply on its own. Okay? The biggest cause for a refrigerant charge in a fixed orifice metering device or a cap tube, a non-adjustable, non-self-adjusting metering device, looking like it is too much in the system, is a clogged evaporator coil or a non-working or badly working evaporator fan or lack of airflow someplace. That is our biggest issue with people thinking they need to remove refrigerant. It has to do with airflow through the coils. Okay, if you're in a residential environment and you end up with this situation, hey, go change the filter. Find the extra filter that someone may not have realized is in the system. It happens. Okay? Ask the homeowner, have you closed off vents? Have you closed off the registers in any rooms? It's an amazing thing as people's kids go away to college or move out. People close their rooms off thinking they're saving money, closed all the vents in the rooms, put a carpet over the vent to make sure that we aren't wasting cooling by cooling the room that's no longer needed. Okay? Well, all of that changes the airflow across the coil. It might look like the coil has too much refrigerant in it, and it really doesn't. So be careful when you have to remove a charge. Okay, the difference between the temperature of the refrigerant boiling in the evaporator and the temperature at the evaporator outlet is known as the evaporator superheat. Okay, evaporator superheat. It's taken at the evaporator outlet. When measuring evaporator superheat on a commercial system with a long suction line, they say that the pressure reading should be taken at the evaporator outlet, not the compressor inlet. I've never seen this done, but it has appeared on exams. So again, when measuring evaporator superheat on a commercial system with an extremely long suction line, they want you to take the pressure reading at the evaporator outlet, and there's usually a pressure port there. There's a Schrader valve there or something, not at the compressor inlet. And again, it's because of that 2 psi or the pressure drop in the line set. Okay. Superheat measurements are best taken with the system operating at design conditions. What do we mean by that? What do we mean by taken at design conditions? Okay. Is my superheat... Go ahead.
Taken at the manufacturer's specs?
Yeah, and it goes along with what you just said. When I'm talking design conditions, if I've gone out and repaired someone's air conditioning and the house temperature is 95 degrees and the system is normally designed to run at 75 degrees, are my superheat measurements going to be all that great before the system returns down to 75 degrees?
No.
Yeah, that's what I mean. So if you go out and repair a non-working system, be careful on doing anything with the superheat readings on that service call. Think about it, okay? And sometimes it's worthwhile, if you suspect there's a problem, it's worthwhile to say, okay, I got your system up and running, but we are going to need to come back and do a follow-up check just to make sure everything's working okay. And you put that on your service slip, and hopefully your dispatcher schedules it. Because, again, when you are at a very hot environment for air conditioning, okay, that coil is under such load, it's not going to have good superheat readings. Just won't. Evaporators can be multi-pass. This means that the coil has been folded over on itself, or is usually 2 or 3 coils clamped together and fed by a distributor. When an evaporator coil is multi-pass and has a superheat reading higher than others, okay, in other words, every pass can have a separate superheat reading, you got to start looking for a block distributor or a dirty coil section. Okay, this can sometimes be very difficult. The only thing I can suggest is look for ice. Ice on the distributor tubing will show you if there's a block in a certain tubing. So that distributor was that octopus-looking thing that I showed you the other day. Okay, if one of those distributor tubes has ice building up on it and the others don't, I have a blockage someplace in that tube. Ice is a very good sign of blockage. Okay, just a word from the field there. Evaporators that are used to chill liquids, like the ones found in Slurpee machines. You're going to go into this when you go through refrigeration a little bit more. Okay, can have superheat measurements, but not be cooling properly. Okay, on the liquid side of the evaporator, you can have mineral deposits build up, and there could be poor circulation on the liquid side. Again, I'm not worried about that right here in air conditioning unless I'm using a chilled water system, which we still have to talk about those evaporators. But for forced draft, if I have superheat readings that are not right, I would probably look at the airflow before I would look at anything else. Okay? Questions? Any questions on how to get superheat? Okay, so everybody on the call understands how to get superheat. That is awesome. Okay, let me pull up SimuAir. Okay, there's enough videos out in the announcements for this course, the announcements for last course, that everybody should be able to get to this point. Okay, I have a real problem repeating myself with videos that I've taken the time to make, so we're just not going to do that. Okay, my screen is a little bit big on this. Hang on a sec. Okay. We're just going to have to deal with the fact my screen's a little bit big for this. Okay. One of the first things we ask you to do, and hopefully this gets a couple people over the stuck point they're at, we asked you to go into equipment, and I asked you to change from a packaged unit to a split system. I don't have the lab in front of me. Did I ask you to change to 410A, or did I say leave it on 22?
No, just say it like that. Just explicit.
Okay. Thank you. Okay. Once you've done that, you go to equipment specifications. Now, equipment specifications are a little bit weird. Okay, I asked you for things like condenser fan amperage, evaporator fan amperage. I asked you what the RLA and stuff like that is, but it's the amperage that's right here on the side, 2.0. Amperage of the compressor is given as 2 numbers, 17 FLA and 75 LRA. Okay? Doesn't tell me the type of condenser fan or evaporator fan, but you can figure that out if you go look at the electrical, which I'll show you in a minute. Okay, tonnage on my call, one of my calls earlier this week, I told you just to use for horsepower, write in the 3-ton or the 3600, okay, or 36,000. The 3-ton system. Okay, tells you the cut out and cut in of the pressure switches, tells you the type of the metering device and the type of the refrigerant. Now, on your lab, you have a 3-column chart. You're not going to fill all 3 columns in at the same time. You have to follow the directions on the lab. Because of what it has you do, it has you go, oops, let me get rid of that, has you go into the simulator, and it has you run it first in a non-fault condition, okay? It has you run it it has you run the simulator just as it is. Okay, so if I want to go in and, actually, this is why I hate doing this. There we go. Run normal. Okay, it says do the first one with the power shut off. So you go to electrical, and you're going to use your meter, okay, and you're going to go through here and take readings with the power off. Now, some readings may not let you take it if you're on the wrong simulator. I got an email from someone yesterday that it wouldn't let you take a reading. Okay, well, the part wasn't even there. Okay, so now, if you look at your outdoor fan and your indoor fan motors, what type of motors are those?
Capacitor start motor, right?
It has a capacitor. Is this a start cap or is it a run cap?
A run.
Yeah, it's a run cap. Why do I know it's a run cap?
Shit.
Are there any starting components around it? Is there anything to take it out of the circuit?
No.
Okay,
Start relay?
There's no start relay around that capacitor on the OFM and IFM.
Yeah. Oh, okay. No, I thought I was thinking of the compressor.
No, I was talking OFM and IFM. So there's no start relay around OFM and IFM. So what type of motor is that?
That's a split capacitor.
So what are the initials for it?
PSC.
It's a PSC motor. That capacitor is always in the circuit. What type of capacitor motor is that? Compressor. We have 2 capacitors. One is taken out of the circuit, one is left in the circuit.
It's a capacitor start.
CFCR.
Yeah.
Capacitor start, capacitor run, also sometimes shortened just to CSR. Okay? When you take your meter readings, all you're doing is clicking on you can click on your ohm meter. Once you put one lead in, once you put your meter in to get your first reading, you can just click on the meter. Okay, and you can find all your other points.
See, that's where I was having trouble at yesterday.
Yeah, you can just click on your meter. Now, again, when you're driving the mouse around on your iPad screen, make sure the mouse pointer, not your finger, okay? Make sure that mouse pointer is over it before you tap on your screen.
Yeah, they didn't say that in the notes because sometimes it's hard to see that little arrow on the screen.
Yeah, I think I put that in my video, but just again, for everybody here, make sure your mouse pointer is actually on the meter. To get rid of your meter, just clear and OK. Okay, do the same thing with your voltmeter. Once you put it in the circuit, you can click on it and find all your other points. Okay? A lot of different points in here. Does anybody know why I'm having you go through this and get your initial readings? There's a reason behind my madness. Does anyone want to guess? Anybody?
Don't know how to trouble.
So we can see the normal conditions and have something to compare abnormal conditions to.
Yeah, starting next week, I'm going to start tossing some faults in here. Stuff we've talked about is going to start showing up in the simulator. Listen, there's things we can train for you guys on, and there's things we can't when we're in the shop environment. I cannot short out compressors for you in the shop environment. I cannot do stuff that is breaking equipment in the shop environment. Okay, I can show you guys how to recover refrigerant. I can show you guys how to take readings. I can show you guys how to install equipment. But there's a problem breaking equipment in the shop environment. Sometimes that can cause a dangerous condition. Okay, sometimes it's very expensive. I can't short out compressors. Okay, and it's impossible to simulate shorting out a compressor. So safely. I could do it, but safely is the question. So the reason we use the simulators, okay, even though it is not a piece of equipment in front of you, is very simple. Okay, I want when you go in the field and come across a problem, I want you to say, wait a sec, I want you to think to yourself, wait a sec, I saw that on a simulator, at least I know where to start looking. To get back to the mechanical section, okay, you just click on the little gear that's up in the top right corner, and I didn't show that, but to flip back and forth, there and there. Okay, to exit back to the main menu, you can use the door. Now, when you start doing diagnostic and repair, we make this relatively easy for you. There's a little tool, and if you hover over it, it says diagnostic and repair. You basically look at the symptoms. What's going on? What's wrong? Okay, so if I have high head pressure, I select high head pressure. Okay, and I can click on the possible cause, and if I have a fault in the system, right now I don't have any fault in here, but you have the ability to test it. It tells you how to test. Okay, once you've tested it, and you're sure it's the problem, do your repair. Once you've done your repair, you have to make sure the system runs. Again, you're not going to do a repair in the field without making sure the system runs. Okay, so you make the system run. Again, on this list here, the symptoms chart, if you have a situation, okay, you select the symptom, you get your possible cause, you can actually click on symptoms to get back to the list, okay, if you chose the wrong one. When you make your repair and you're sure the system is running the way it's supposed to be running, you use the little door to go back to the main menu. Okay, if there's a fault in the system, it's going to pop up. It's going to tell you if the system was repaired or not repaired. If it's not repaired, you've got to go in and try again. Everything you do is logged. Please use your test tools and don't just guess on repairs. Okay, that's not the purpose. The purpose isn't how fast you can run through the faults. I'd rather have you take your time and do it right and get it on the first try than just replace parts. Okay? Any questions on the simulators that I need to answer for you guys?
What's the sequence of operation for that?
Well, when you're running it, sequence of operation, you're going to find out. You're going to turn on the thermostat. Thermostat calls for cooling. You're going to look at the electrical side and see what happens. Okay? I've given you the sequence of operation in the last course. I actually wrote this out. Remember, this is an advanced course. You had to do everything in the core course to be successful in this course. Okay? Some of this stuff, as with anything in HVAC, is you have to be able to look at equipment, look at schematics, and look and see what's happening and translate it into English. Okay, you've got to be able to do it. That's sequence of operation. Look at the schematic and what opens and what closes. Okay, there's no writing on here that tells you what the sequence of operation is. That's part of learning the system. You've got to look at the system and you've got to figure out what the sequence of operation is. Thermostat calls for cooling. This closes, this gets energized, this runs. Thermostat satisfies what opens, what closes, what is energized, what is de-energized. Sequence of operation. Okay? Not going to hand it to you. You've got to figure it out. Any other questions on simulators? Okay. I have email, folks. Use it if you need it. I may not answer. I may not give you the answer, but I will lead you in the right direction. Okay? If I just give you the answer, you guys don't learn anything when it comes to this. I need to lead you in the right direction. It's important. Question on EPA. Anything that's come to mind since I went over it earlier? Questions on EPA. Anything? Any other questions on anything I've gone over this week? Okay, that's all I have for today. You folks have a great day. If you need, there was someone who needed to talk to me, hang out, hang up.